Looking at the last term question, it says, how can the melting point of a solid be used to determine its purity? We know a pure substance has a very specific, exact melting and boiling point. So, for example, water boils at exactly 100 degrees if it is pure. So what we would do is we would melt the substance and see if it melts at a very specific temperature and compare it to a database of known melting points. So compare it, Google online, and research its known melting point to see if it matches up to the true value. Last month says, why are atoms neutral? Well, we know there are positive protons inside the nucleus, and we've got negative electrons orbiting the nucleus in our shells, and we know the number of protons and electrons is the same, so they cancel each other out, which means the atom is overall neutral. Last week says, why is oxygen a gas at room temperature? If something is a gas at room temperature, that's because it has a low boiling point, so it's quite easy to turn it into a gas. So the question is really saying, why does oxygen have a low boiling point? Well, that's because oxygen, O2, is bonding between two non-metals, so it has simple molecular bonding, which means we've got weak intermolecular forces between the molecules which require a small amount of energy to overcome. And then you asked, can metallic sodium by itself conduct electricity? So sodium exhibits metallic bonding, and we know metallic bonding has a sea of delocalized electrons which can move and carry a charge. Therefore, all metals, including sodium, can conduct electricity. So the last topic that we need to discuss is this idea of bonding models. So far, throughout all of our lessons, everything we've looked at has used or involved the use of models in chemistry. And the reason we use models is because, unlike the other sciences, we're unable to see the particles that we're talking about. So we can't see the atoms, the ions, or the electrons which we're trying to describe. So we have to use diagrams and images in order to understand how they move and how they behave. So if you think back to states of matter, we use the particle model to explain how the particles behave when you heat them up or cool them down. And the problem with that model was that we know particles aren't perfect spheres, and it ignored forces between them. If you think of atomic structure, we use a model of the atom to explain the orbit of the electrons around the nucleus and the protons and neutrons inside the nucleus. But again, we know that model was flawed because electrons don't orbit in perfect circles. So the images we use usually imply that they are 2D, and we know most of the atom is empty space, and our models don't draw that. So for each of the models we've looked at, we need to think of the advantages of using them and the disadvantages. So what do they show us, but what do they fail to show us in their detail? So in this topic, we'll have used or come across 4 different types of model that we need to be able to evaluate. And this did come up about 2 years ago in the GCSE exam as a 6-mark question. So it's really important that you're familiar with the limitations and advantages of these different types of model. So we've got dot and cross, which we've used to draw our diagrams. We've got ball and stick, which hopefully you've come across in lessons by using the Mollymog kits. We've got our stick diagrams, which are like dot and cross, but 2D, and use a stick instead of our dots and crosses to show our electrons. And we've got our giant ionic lattices, so these 3D solid structures. So pause the slide and have a go at thinking of some advantages of using each of these models and some disadvantages of using these models in science. So if we look at the dot and cross diagram, advantages include the fact that they clearly show where the electrons come from. So they show crosses for the hydrogen electrons and dots for the nitrogen electrons. So we can see where those electrons go, where they move, and where they come from. So it's really clear at showing us electron transfer. However, it doesn't show us the size of the atoms. So on this, you might think nitrogen and hydrogen are the same size because these circles have been drawn the same size. And it doesn't show the shape in 3D. We know these molecules don't exist in the 2-dimensional plane. They are 3D molecules. So the better model will show us them in 3D. If we move on to the ball and stick then, the advantages are that it will show us in 3D, so you can see how those atoms arrange around that central blue atom. And it does show generally those sizes, so you can clearly see on this diagram, this blue atom seems to be bigger than these 3 grey atoms. So it does show relative sizes quite usefully. It doesn't show you how electrons move, so it doesn't show you where the electrons come from and how they're transferred. And it does show the atoms further apart than they are, so these lines isn't actually accurate. It shows an inaccurate distance between each of the atoms. If we look at our 2D stick diagram, it's a very simplified version of the ball and stick model, so it's really simple and easy to understand and represent covalent bonds. And they do tell you what type of atom, so I've got 1 nitrogen and 3 hydrogen, so it tells you the ratio of the atoms, what atoms in the bond and how they're all connected. The problem is, it doesn't show anything about the size of the atoms, it doesn't show anything about the 3D representation in space. So it is a very limited and simple model. And if we look at these 3D ionic solids, obviously the advantages if we've got this depiction in 3D, so we can clearly say it's not flat, it's not a 2D molecule like these shouldn't be. It does show you the repeating pattern in a giant lattice structure, so it shows you you've got positive surrounded by negative ions, surrounded by positive, surrounded by negative, so it shows you that layered alternative structure with many, many, many ions, which is exactly how it should be. The problem is it only shows you the outer layer, you can't see the inner layer. It also shows them as being the same size. However, it's very, very rare you would get ions that are the same size because you have a different number of electrons and a different number of electron shells. So the main disadvantages of this one is that the ions should be different sizes.